Good morning, all of you. Today, my subject is organic chemistry. My chapter name is organometallic compounds. Organic compounds in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metals, example lithium, sodium, magnesium, zinc, mercury, lead, cadmium, etc., form such compounds. The organic part is generally an alkyl, alkenyl, or aryl group. They are named simply by adding the name of metal to the name of the organic group linked to the metal. For example, CH3Li, ethyl magnesium, N-butyl lithium, diethyl mercury, tetraethyl lead, phenyl lithium, dimethyl cadmium, diethyl zinc. The carbon metal bond is organometallic compounds differ widely varying from bonds which are essentially ionic to those which are largely covalent. Thus, the extent of the ionic or polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the metal, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows as sequence: carbon potassium, carbon sodium, carbon lithium, carbon magnesium, carbon aluminium, carbon zinc, carbon cadmium, and carbon mercury. The reactivity of organometallic compounds also depends upon the nature of the carbon metal bonds. Generally, the larger the ionic character of the carbon metal bond, more is the organometallic compound. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selectivity nature of the reactions. Organometallic compounds are extremely useful for the synthesis of vast variety of organic compounds. Apart from these, many of the organometallic compounds are commercially important as well. For example, tetraethyllead is extensively employed as an anti-knock compound. Organonotion compound are used as antioxidants in rubber products. Phenyl mercuric acetate is used as a fungicide and a disinfectant, and organoarsenic compounds are used in medicines. Organomagnesium compounds, Grignard reagents. Organomagnesium halides are extremely important reagents in synthetic organic chemistry. These reagents are commonly known as Grignard reagents after the name of the discoverer Victor Grignard, who received the Nobel Prize in Chemistry in 1912 for this discovery. The general formula of Grignard reagent in RMGX or ARMGX, where R represents an alkyl and AR represents an aryl group. Preparation: Grignard reagents are prepared in the laboratory by the action of an alkyl or an aryl halide on magnesium metal in dry ether. Besides ether, tetrahydrofuran, dioxane, dimethoxy, ethane or dimethyl ether of the diethylene glycol, tertiary amines, etc., can also be used as solvents. In fact, THF is considered to be best solvent since it increases the reactivity of an alkyl or aryl halide towards magnesium. It is because of this reason that the Grignard reagents of less reactive aryl and vinyl halides. Further, it has been found that for a given alkyl group, the ease of formation of Grignard reagents is the order iodide greater than bromide greater than chloride. The alkyl or aryl magnesium fluorides are, however, unknown. For a given halogen, the order of reactivity is CH3x greater than C2H5x greater than C3x5 and so on up to etc. That is, the formation of Grignard reagent becomes increasingly difficult with increase in the number of carbon atoms in the alkyl group. The use of tertiary alkyl iodides is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chlorides may then be used. Procedure for the preparation of Grignard reagents: alkyl or aryl halide is added slowly to a perfectly clean and dry flask containing dry magnesium turnings covered by a layer of absolutely dry ether or THF. The reaction mixture is warmed a little when an exothermic reaction should soon start. If the reaction does not start within 5 minutes, a few crystals of iodine are added and the reaction mixture is warmed a little. A vigorous reaction soon sets in and magnesium gradually dissolves, forming a cloudy solution of Grignard reagent. Precautions in the preparation of Grignard reagents. During the preparation of Grignard reagents, the following precautions must be observed. The first, apparatus should be perfectly dry and protected from moisture by using a CaCl2 guard tube. Second, all the reagents and solvents, that is alkyl or aryl halide, Magnesium metal and ether must be absolutely dry. Third, ether used as solvent must be completely free from alcohol. This can be done by the first washing ether several times with water, following by drying over anhydrous CaCl2 for 1-2 days and subsequent distillation over sodium. An atmosphere of dry nitrogen throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by moisture and react with oxygen and carbon dioxide to form alcohols and carboxylic acid respectively. The ethereal solution of Grignard reagent thus obtained is generally used as such for a various reaction by adding to it the other sub-reagent. The mechanism of formation of Grignard reagent is still not certain. According to Gomberg and Beckman, the reactions commences with the formation of a small amount of magnesium halide and then proceeds by a free radical mechanism. Rx plus Mg plus Xr gives Rr plus Mgx2. Mgx2 plus Mg gives 2 Mgx free radical. Rx plus Mg free radical X gives R radical plus Mgx2. R radical plus Mgx gives Rmgx. This mechanism also elegantly explains the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium and iodine. Structure of Grignard reagents. The structure of Grignard reagent has not been finally settled so far. The recent search has shown that the actual structures varies with the particular Grignard reagent and the solvent used for its preparation. Grignard and Blaise observed that evaporation of ethereal solution of Grignard reagent resulted in a white solid having the composition RmGx.2C2H5 They suggested that ether molecule were present as ether of crystallization. X-ray analysis of these dietherates suggests that the four groups are arranged tetrahedrally as shown in formula. Thus, formula suggests that ether does not merely provide a medium for the reaction, but it is also helped to dissolve the Grignard reagent formed due to solvation by ether molecules. This is supported by the observation that Grignard reagents can be prepared even in benzene solution in presence of tertiary amine, which coordinates with magnesium like ether and thus dissolve it. Further, formula shows the Grignard reagent in a monomeric form, but physical studies have revealed that Grignard reagents exist as 1:1 complex of dialkyl or diaryl magnesium and magnesium halide coordinated with molecules of ether. These two species are held together by halogen bases. Reactions of Grignard reagent. The carbon magnesium bond is a Grignard reagent is highly polar due to the large electronegativity difference between carbon and magnesium. Consequently, due to greater electron density around carbon, the alkyl group in Grignard reagent can act as a carbon anion or a nucleophile, that is, it can attack any electron deficient center in the other molecules. In other words, Grignard reagents chiefly undergo nucleophilic substitution or nucleophilic addition reactions. First, nucleophilic substitution reaction. The Grignard reagents react with the compounds containing an active hydrogen or halogen atom. All such reactions involve the nucleophilic attack of the alkyl group of the Grignard reagent on the electron deficient. Second, nucleophilic addition reaction. Grignard reagents react with compounds having a multiple bonds such as CO, CS, CN, SO, etc. to form addition products which when hydrolyzed yield a vast variety of compounds. In all such reactions, the addition of the nucleophilic group of RMGX, that is R negative, occurs at the more electropositive end, and that of MGX group at the more electronegative atom of the multiple bonds. Synthetic use of Grignard reagents. Grignard reagents serve as extremely valuable starting materials for the synthesis of vast variety of organic compounds. They have attained a position in synthetic organic chemistry unrivaled by any other class of compounds. To illustrate this, some important synthetic application of Grignard reagents are described below. First, alkenes. Alkanes, by action with active hydrogen containing compounds. Active hydrogen containing compounds such as water alcohols, thioalcohols, carboxylic acids, hydrogen sulfide, ammonia, amines, terminal alkynes, etc. react with Grignard reagent to form an alkane corresponding to the alkyl or aryl group of the Grignard reagents. Since methane is evolved quantitatively when CH3MJ is treated with compounds containing the alkenes. By action with the reactive alkyl halide, Grignard reagents react with reactive alkyl halides such as 1-butyl chloride, benzyl chloride, etc. to form alkenes. Alkenes. Grignard reagents, being weak nucleophiles, do not react with simply alkyl halides. However, compounds containing more reactive halogens such as allyl iodide, etc., react with them, giving alkynes. Grignard reagent react with the terminal alkynes, forming alkynyl Grignard reagent with upon treatment with alkyl halide gives higher alkynes. Fourth, primary alcohols by action with ethylene oxide following by hydrolysis. Grignard reagents react with ethylene oxide to form addition products which on hydrolysis with dilute hydrochloric and acid form primary alcohols containing two carbon atoms more than alkyl halides. Sec B. By action with formaldehyde followed by acidic hydrolysis. When treated with formaldehyde, Grignard reagent forms an adduct which on hydrolysis with dilute hydrochloric acids give primary alcohol. C. By action with oxygen. Primary alcohols are formed by passing dry oxygen through the solution of Grignard reagent followed by acidic hydrolysis to the resulting addition product. Fifth, secondary alcohols by action of aldehydes other than formaldehyde followed by acidic hydrolysis. By treating an excess of Grignard reagent with ethylene formate, this reaction takes place into two steps. First, Grignard reagent reacts with ethyl formate to form an aldehyde, which in turn reacts with another molecule of Grignard reagent to yield an adduct which forms a secondary alcohols on hydrolysis. Tertiary alcohols by action with ketones followed by hydrolysis give tertiary alcohols. Secondary tertiary alcohol having at least two similar alkyl groups may be prepared by the interact between an ester other than formic ester and excess of a Grignard reagent. By a reaction with acid chlorides and acid anhydrides, Grignard reagents 2 moles react with acid chlorides or anhydrides 1 mole to give addition product which upon hydrolysis give tertiary alcohols. 7. Ethers. The Grignard reagents react with the lower halogenated ethers to give higher ethers. Monochloromethyl ether reacts with Grignard reagent to form ethyl methyl ether. 8th, aldehydes. When a Grignard reagent is treated with ethyl formate 1 mole and aldehyde is formed, however, with excess of Grignard reagent, the product obtained is secondary alcohol. B. Aldehydes are obtained in better yielding if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetal in the case of prevents for formation of secondary alcohol. Aldehydes may also be obtained by the interaction between a Grignard reagent and hydrogen cyanide. Ninth, ketone by treatment with alkyl cyanide formed by the acidic hydrolysis by action or with acid chlorides. As discussed on page 83, equimolar amounts of Grignard reagent and acid chloride give an addition product which forms ketone on hydrolysis. If Grignard reagent is used in excess, tertiary alcohols are obtained as ultimate products of the reaction. 10th, monocarboxylic acid. Grignard reagent interact with dry ice to form addition products with an acid hydrolysis give monocarboxylic acids. 11th, esters. By action with the ethyl chloroformate, equimolar amounts of Grignard reagent and ethyl chloroformate react to form high esters. Thioalcohols. Grignard reagents react with sulfur to give an addition product which gives a thioalcohol on hydrolysis. RMGX plus H gives addition product upon hydrolysis gives thioalcohol. 13th, phenol. Aryl magnesium halides react with oxygen to form an addition products which upon hydrolysis give phenols. Phenyl magnesium bromide plus half O2 and in presence of dry ether gives phenoxy magnesium bromides which upon hydrolysis give phenol. 14th, alkyl cyanides. By interaction of Grignard reagent of 1 mole and cyanogen chloride or cyanogen. RMGX plus cyanogen chlorides give alkyl cyanide plus MgXCl. Excess of Grignard reagent is avoided since it will react further with alkyl cyanides to yield ketones. 15th, primary amines. Grignard reagents react with chloramine to form primary amines. RMGX plus chloramine gives RNH2MgXCl. Reasonable yields of primary amines is obtained only with Grignard reagents contain tertiary groups. Primary amines can also be prepared in satisfactory yield so by the reaction of Grignard reagents on orthomethyl hydroxylamine. 16. Sulfinic acid. On passing sulfur dioxide into a well-cooled solution of Grignard reagent, an addition product is obtained which on hydrolysis gives sulfinic acid. Sulfur dioxide plus Grignard reagent gives addition product which upon hydrolysis gives sulfuric acid. 17 dithioic acids. These are prepared by the action of Grignard reagents with carbon disulfide followed by acidic hydrolysis. Carbon disulfide plus Grignard reagents gives addition products which upon hydrolysis give dithioic acid. 16 organometallic compounds. Grignard reagents and inorganic halides interact with each other resulting in the formation of other organometallic compounds. Abnormal addition of Grignard reagents. First, addition of hindered ketones. If the Grignard reagent or the ketone contains branch or at the alpha carbon, sometimes the usual addition reaction does not occur due to steric hindrance. Instead, reduction occurs in which a hydride ion is transferred from the Grignard reagent to the ketone via a six-membered cyclic transition state in a manner similar to the Mann-Penrose-Varela reduction. For example, when isopropyl magnesium bromide is added to the diisopropyl ketone, the expected 3-degree alcohol is not formed. Instead, the secondary alcohol diisopropyl carbonyl is obtained by the reduction of the keto group. Second, addition of alpha beta unsaturated compounds. Alpha beta unsaturated compounds react with Grignard reagent to give 1, 2, and 1, 4 addition products. The orientation of addition is often controlled by steric factors. In general, substitution at the carbonyl group favors 1, 4 addition, while substitution at the double bond favors 1, 2 additions. In most cases, both products are formed, but alpha beta unsaturated aldehydes nearly always give exclusively 1 2 addition products when treated with Grignard reagent. However, the extent of 1 4 addition of Grignard reagents can be increased by carrying out the reaction in presence of cuprous chloride and cupric acetate. Example, this is called conjugation addition and probably occurs in a free radical mechanism. Limitations of Grignard synthesis. Grignard reagent suffers from the following limitation. First, Grignard reagents are sensitive to moisture, oxygen and carbon dioxide and hence must be protected from them. This makes the handling of Grignard reagent difficult. Second, Grignard reagent can't be prepared from alkyl halide containing other reactive functional groups such as OH, SH, NH2, COOH, SO2, CHOC, double bond O, COOR, CEN, etc. Since they all react with them, only alkyl halides containing a few other groups such as ROR, AR, X, etc. can be used to form Grignard reagents. Third, generally branching of the carbon chain nearly functional group prevents a reaction probably due to steric hindrance. For example, CH3MGBr or CH3MGI does not react with ditert-butyl ketone. Similarly, if Grignard reagents contain large alkyl group, the reaction is sometimes prevented again due to the steric hindrance. For example, isopropyl methyl ketone reacts with CH3MGI but not with tert-butyl magnesium chlorides. Fourth, compound which are capable to form Enolization vibrate hydrogen with Grignard reagents. Organozinc compounds. So, although organozinc compounds of the type R2ZN are not commonly used in organic synthesis, they are particularly useful when milder reagents are required. Methods for formation. First, form from alkyl halides. Alkyl iodides react with zinc copper couple in high boiling ether to form alkyl zinc iodides, which upon subsequent distillation in atmosphere of CO2 undergo disproportion of give dialkyl zinc compounds. Second, form from organoaluminium compounds. Treatment of trialkyl aluminium with zinc chlorides give dialkyl zinc compounds. This method forms the basis of laboratory preparation of these compounds. 2.3.2 Physical properties. Dialkyl zinc compounds have linear geometry due to sp hybridization of zinc atom. They are non-polar, low boiling liquids or low melting solids soluble in organic solvents. The lower zinc compounds are highly inflammable in air and hence are usually prepared and used under CO2 atmosphere. Chemical reaction. The chemical reactions of organozinc compounds are similar to those of Grignard reagents with the only difference that they are less reactive. For example, they do not react with CO2 and react only slowly with cyanides, ketones and esters. Some important chemical reaction of dialkyl zinc compound are discussed below. First, reaction with water. They readily react with water to form alkanes. Reaction with alkyl halide. Dialkyl zinc compounds do not react with primary and secondary alkyl halides. They react only tertiary alkyl halides to form alkanes containing a quaternary carbon atom. Third, reaction with acid chloride. They react readily with acid chloride to form ketones. Ketones are obtained in good yield because dialkyl zinc compounds react very slowly with them. Third, Ripon-Sky reaction. When an aldehyde or a ketone is added to the solution of an alpha halo ester in presence of zinc, an organozinc compound is first formed, which then adds to the carbonyl in a manner similar to Grignard reagent to form beta hydroxy acid. This reaction is called Ripon-Sky reaction and is useful for the method of preparing beta hydroxy esters or acids and their derivatives. Iodomethyl zinc iodide. Iodomethyl zinc iodide is an important organozinc compound and obtained by the action of the ZnCu couple on methyl iodides. This reaction is called Simon-Smith reaction and used for preparation of cyclopropane derivatives. This addition occurs in a stereospecific sign manner according to the following considered mechanism. Organolithium compounds. Compounds in which lithium atom is directly bonded to a carbon atom are organolithium compounds. Organolithium compounds are more reactive than Grignard reagents and also undergo a few additional useful reactions. Therefore, they are widely used in organic synthesis these days. Formation of alkyl lithium by action of an alkyl halide with lithium. Alkyl lithiums are generally prepared by treating an alkyl halide with lithium in hexane, benzene, or any other hydrocarbon solvent at a low temperature in any inert atmosphere of nitrogen or argon. For the preparation of alkyl lithiums, hydrocarbon solvents are preferred over the since of the use of ether not only increases Wurtz's reaction but also reacts with it. By metal-metal exchange, alkyl lithiums can be readily prepared by the displacement of one metal by the another. Chemical reactions of alkyl lithiums. The CLI bond is more polar than CMG bond. Therefore, alkyl lithium are more reactive than the Grignard reagents, except a few differences. Their chemical behavior is similar to the Grignard reagents. Some of their most important chemical reactions are resemblance with the Grignard reagent. They resemble Grignard reagents in most of their reactions. First, formation of hydrocarbons. Like Grignard reagents, they react with the compounds containing active hydrogen to form corresponding hydrocarbons. For second, formation of primary, secondary, and tertiary primary alcohols by the action with formaldehydes. Like Grignard reagents, alkyl lithium compounds also react with ethylene oxide to form primary alcohol containing two carbon atoms more than starting alkyl halide. B. Secondary alcohols by action with aldehyde other than formaldehyde. C. Tertiary alcohols by action with ketones. Third, formation of ethers by action with the monochloroether. Monochloroether react with the CH3Li in presence of hexane forms ethyl methyl ether. Fourth, formation of aldehydes by action with ethyl orthoformate of hydrogen cyanide. Fifth, formation of ketones by action with an orthoester other than orthoformic ester or alkyl cyanide. Sixth, formation of nitriles by action with cyanogen chloride. First, reaction with alkyl halides. Alkyl lithium reacts with alkyl halides to form alkanes. Seventh, reaction with aryl halides. Aryl halides undergo nucleophilic substitution reaction by elimination addition of benzene mechanism. Eighth, reaction with the heterocyclic compounds. Heterocyclic compound undergo nucleophilic substitution reaction by bimolecular displacement mechanism. Example, pyridine reacts in presence of C6H5Li at 383 K temperature, goes nucleophilic aromatic substitution here to phenylpyridine. Second, difference from Grignard reagents. Organolithium compounds being more reactive than Grignard reagent undergo some additional reactions are discussed below. First, action with carbon dioxide. Grignard reagents yield carboxylic acid with carbon dioxide while organolithium compounds yield ketones. The difference is due to the reason that organolithium compounds are more strongly nucleophilic than Grignard reagents and thus react further with the intermediate resonance stabilized carboxylate ion giving ketones. Second, action with carboxylic acid. Alkyl lithium compounds react with carboxylic acid yielding ketones as main product. Grignard reagents on the other hand give alkanes corresponding to the alkyl group of Grignard reagents. Third, addition to carbon-carbon double bond. Unlike Grignard reagents, organolithium compounds add to simple alkenes to give a mixture of compounds. The addition occurs at high pressure. Fourth, formation of tertiary alcohols, organolithium compounds being more nucleophilic and smaller in size than the corresponding Grignard reagents add to sterically hindered ketones to form sterically hindered tertiary alcohols. Grignard reagents, on the other hand, do not give such additions reaction. For example, isopropyl lithium adds to dry isopropyl ketone to yield triisopropyl carbonyl. In contrast, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohol is not formed. Instead, reduction of the ketone by Grignard reagent occurs to give diisopropyl carbonyl and propylene. Reaction with the alpha beta unsaturated carbonyl compounds, organolithium compounds being more nucleophilic predominantly undergo 1-2 addition of alpha beta unsaturated carbonyl compounds, whereas Grignard reagents give mainly 1-4 addition products. Hence chapter is complete. Thank you.